Okay, welcome everybody. We start with the second part of our workshop on machine learning in quantitative finance and risk management. And whereas the first part was on early exercise options, neural networks, valuation adjustments, we now move to some broader topics, more different topics in the second part of this workshop. And we start with Anastasia Borovykh. She is a postdoc at Imperial College, London, and she works on understandable machine learning techniques. She got a PhD in mathematics from the University of Bologna, and before that she did a postdoc in the CWI with us. And she will talk today about to interact or not on the convergence properties of interacting particle optimization. Anastasia, are you there?
Yeah, I'm here.
All right, there you are. Hi.
Hi.
So the floor is yours, so you can start screen sharing and present your work.
Can you see my screen?
Yes, it's full screen and it's well visible. All right, floor is yours.
Perfect. Okay, so what I want to discuss in this presentation is a bit of a more broad topic, not necessarily related to finance, but kind of more related on the optimization properties that we use in neural network optimization, machine learning in general. And in particular, the topic will be about interacting particles, so optimization using interacting particles, and I will discuss their convergence properties and also kind of a variance reduction that they achieve. So it's worked together with my supervisors at Imperial panels, Nick and Greg. So what's the kind of optimization challenge in deep learning? Well, in deep learning, we typically have a very non-convex loss surface, something like what you see in this picture. And we are looking for optimization algorithms that are able to kind of find a good minimum in this optimization objective. So what is the goal of a good optimization objective? Well, one, we want it to be controllable. So we want to understand how can we change the hyperparameters of our algorithms such that it converges to a good minimum. We want it to escape local minimum saddle points. And like I said, converge close to the actual optimum. So what I will discuss in this presentation, first of all, I will present the general optimization objective. So what are we trying to optimize? Then I will discuss several classical optimization schemes that are used to optimize these kind of objectives and their convergence results. And related to this, also kind of a challenge or a problem with one of the optimization algorithms, in particular stochastic optimization. And then I will present the optimization algorithm that we kind of proposed in this work, which is using interacting particles and the convergence properties of using these interacting particles. And then I will finish with some numerical examples and kind of present some further ideas as to why the optimization algorithms and the problem that we study is actually interesting also in other applications. All right, so the objective that we have in this paper is kind of a generic one. We want to try to solve a constraint optimization problem of the following form. So our goal is to minimize some function f of x, with f being our objective function, which in the theoretical results, we take it to be Lipschitz and either strongly convex or just convex. And x, the curly x, is our constraint set. So we want our x to lie in this constraint set. And we are looking for the minimizer x star of this objective function. Now, one way of optimizing such a problem is using projected gradient descent. So the way that works is at every time step, we take a step into the direction of the negative gradient of our objective function f. And then we project back into our constraint set using this projection operator by curly x, with by curly x being the closest value to our value x in L2 norm. So we are defining the projection through the Euclidean L2 norm. The drawback of such a method is that we are kind of tied to the fact that we are using this L2 norm. So we are tied to this Euclidean projection. So for example, what this can mean is that if we have a constraint set, which is depending on the dimensionality. So if we, for example, have this property here so that the the distance between 2 points in our constraint set x and x thing is dependent on the dimensionality, then it means that our convergence rate is also going to be dependent on the dimensionality, which obviously, if our problem is high dimensional, is not something that we want. So as a kind of generalization of this projected gradient descent, mirror descent was introduced. For those that have never seen mirror descent, it might look a bit confusing, but it's not. Basically, what happens in mirror descent is instead of using this L2 projection that we'd had in the projected gradient descent, we use a more general thing. In particular, the projection is done using something that's called the Bregman divergence. And the Bregman divergence is defined through this phi, which is the mirror map. So essentially what happens in mirror descent is we have some value xk, which is in our constraint set. We then project it using the mirror map into our unconstrained dual space. In this dual space, we update it using our gradient of the objective function f. And then we project it back into our constraint set here, now not using just the Euclidean norm, but using this Bregman divergence, d phi. So what is the benefit of mirror descent? Well, essentially the benefit is that we are free to choose this mirror map phi as we want. So if we can find a phi such that this kind of size of our constraint set with the size being defined using this Bregman divergence is sufficiently small, or for example, dimension independent, then we can obtain a faster convergence than we did with projected gradient descent, where remember that this thing was tied to the Euclidean L2 norm. So that's the basics on mirror descent. In our paper, we consider a continuous version of mirror descent, where essentially we have this variable z being updated using the negative gradient, and the projection is being done using this mirror map phi, but just in continuous time. Like I said, if we were to prove the convergence of this continuous time mirror descent, what we would obtain is something like this. So it converges linearly in time. And this d phi curly x is this this thing which I kind of call the size of our constraint set, where the size is measured using this Bregman divergence. So as I said before, if we can choose a mirror map phi such that it adapts well to our constraint set curly x, then mirror descent can achieve a faster convergence than projected gradient descent. So this is the big kind of good thing about mirror descent. Now, the thing that we are looking at in this work is that sometimes the gradient estimate, so this gradient of our objective function f, it can contain some noise. So in particular, this is common if we were to compute it over a batch size of our data, so not using the full batch gradient descent, but mini batch gradient descent. Then under certain assumptions on this noise, and again, working in continuous time, we can rewrite our optimization algorithm as stochastic mirror descent, where in addition to this gradient step, we now also have this noise term. And again, the projection is done into using the mirror map phi. So what is kind of the challenge of this stochastic mirror descent? Well, we are not actually able to converge directly to our optimum. So the distance to optimality, so the distance between our objective function f at xt and our objective function f at our optimum x star, is bounded in the following way. So this first term is kind of the term we saw also with regular mirror descent, which converges linearly in time for a convex function. But we also, in addition, have this second term, which is the noise term. So our algorithm only converges to a neighborhood of our optimum, and the size of this neighborhood is controlled by this noise variance sigma squared. So the more noise, the further kind of away in expectation we converge to the optimum. Now, we're not the first ones to notice this problem. In particular, various techniques have been proposed to reduce this variance, so reduce the effect of this noise. One option is to increase the batch size, so to make the gradient estimates more exact, which amounts to essentially decreasing the noise variance over time. It could also decrease the learning rate. Various kinds of importance sampling techniques have been proposed, or other kinds of variance reduction techniques. And in this paper, or in this presentation, we propose to take a different approach. We propose to use something we call interacting particles. So what is interacting particles? Well, typically, when we optimize an objective function f, what we do is we take some initial value, some initial condition x0, and then we run just one optimization algorithm using the gradient of our objective function f. What we propose to do is we propose to start with many particles, in particular capital N particles initialized in different locations in our objective space. And we let each of these particles run their own optimization, but in addition, we also let these particles interact. So the way this looks is, as this formula shows, we have N particles ZTI, with I being 1 to N. They're all taking a step into the direction of the negative gradient of our objective function f, but they're also interacting with each other through this second term. So essentially, A represents our interaction matrix, with Aij being 1 if two particles are interacting, or in other words, exchanging their values. And then this parameter theta is controlling the interaction strength. So the higher this theta is, the more value we are putting on having the particles exchange their values, and in other words, converge to the same value. And then again, of course, each particle is driven by its own Brownian motion noise. So yeah, if we can also rewrite this algorithm in vector form. The reason that this is interesting is that our convergence will kind of depend on how our particles are connected. And the connectivity of our particles in this vector form is represented using this graph Laplacian of our interaction matrix. And in particular, how much the particles are interacting is represented using its eigenvalue. So our convergence result will in particular depend on this underlying lambda, which represents the first non-zero eigenvalue of our interaction matrix, of our Laplacian of our interaction matrix. So that's all for this slide. So what we then obtain, if we are to kind of prove the same convergence as we did for the regular mirror descent algorithm, then we are left with this bound. So the distance of our particle f evaluated at point xt to our function f evaluated at our optimum point x star is bounded using these 4 terms. So what are each of these 4 terms? Well, the first one is this one, which is the same as we saw in regular mirror descent. It's the standard optimization error, which converges linearly in time, with this the second thing, d squared, again representing kind of the distance of our constraint set curly x. Now the second thing, which is the interesting thing, is our variance term. So if you remember, for our regular stochastic mirror descent algorithm, this was given by sigma squared times this L infinity norm of our mirror map, but now it's actually reduced by a factor of n. So if we use these interacting particles to run n instances of the algorithm and let the particles interact, then we can actually decrease the variance by a factor of n. And these last 2 terms, this expected value of tilde z, this represents the deviation from the particle average. So what we see here is that if we can show that this fluctuation term, so this deviation from the particle average of each individual particle, is sufficiently bounded, then actually we can obtain a reduction in the variance. So something that was obviously our goal to achieve, because then we can converge closer to the actual optimizer of our objective function f. Now, luckily, it is the case that actually indeed our fluctuation term is bounded under certain assumptions. In particular, what we can do is we can derive the following bound on our expected value of the sum of these fluctuation terms. So just to reiterate again, each of these fluctuation terms represents the distance of our particle ZTI to the average, so the average of all of our particles. And like I said before, if this can be kept small, then indeed we will obtain a variance reduction. So we will converge closer to the optimum. So the bound that we see here is, first of all, we have this term which is converging exponentially in time if we take f to be a strongly convex function. And then the second term is this thing here, which from this we see that it's not increasing in n. So the more particles we have, this kind of remains bounded. And also the variance term, again, is decreased if this thing is sufficiently large. So what is this thing? Well, in this thing, we see first of all our theta, which is our interaction strength. So first of all, if we impose a sufficiently high interaction strength between the particles, then this term will be sufficiently small. Obviously, this makes sense because, like I said, imposing a sufficiently high interaction strength means that we are putting a lot of value on the particles exchanging their values. So in other words, we will converge closer to all particles having the same value. The second thing we see here is our kappa, which is our strong convexity constant. So the more strongly convex our function is, the smaller this term will be. And the third thing is this underlying lambda, which represents the type of interaction. So as I said, if the interaction is sufficiently dense, so if sufficiently many particles are at every time point exchanging their values, then this thing will be relatively high. And in other words, this fluctuation term can be bounded. So to conclude, what are the benefits of this interacting stochastic mirror descent? Well, as I said, the problem with stochastic mirror descent is that, or with stochastic optimization in general, is that we are only converging to a neighborhood of the optimum, and the size of this neighborhood is dependent on how much noise we are adding into our algorithm. To reduce the effects of this noise, you can reduce the noise variance, decrease the learning rate, these kind of things, but they obviously also come at a additional computational cost. So we propose to do interacting stochastic mirror descent. So instead of just running one particle, we run n particles, and we let each of these particles exchange their values. So what we then see is that if we take a sufficiently large amount of particles n, if our function is sufficiently strongly convex, or the interaction strength between our particles is high enough and the interaction between the particles is dense enough, so sufficiently many particles are exchanging their values, then we can obtain that the variance is reduced by a factor of n, so how many particles we have, if we compare this to just running one particle or running IID particles, so particles which are not interacting. So that's the first result. What we can also do is kind of look at it from a bit of a different perspective. In particular, we can look at the convergence results from a sampling perspective. So what is the goal in sampling? Well, the goal in sampling is to run a stochastic differential equation, which at some point will converge to samples from some invariant distribution, which is the distribution that we want to sample from at some point. So what we see is that for our interacting stochastic mirror descent, if we run our algorithm long enough, our samples will be from the invariant distribution eta infinity. So with this distribution being defined in the following way, so this is our objective function, and this is our interaction part. Now, the interesting thing is that if we have converged, so why is this sampling view even relevant? Well, the point is that if we have converged to samples from our invariant measure, then actually the mode of this invariant distribution, so kind of where our particles are most concentrated at, is exactly the optimum of our objective function, so the optimum of our objective function f. So in particular, if we were to make this a bit more rigorous, finding the mode of our invariant distribution will be equivalent to solving the following optimization problem. So it's the same as finding this minimizer of this w, where this w is defined as this thing. And now, because of the fact that our interaction is defined in a certain way, this is the same as simply finding the optimum of our objective function. So if our samples have essentially converged to samples from the invariant measure, so if we have sampled sufficiently long from these using this interacting stochastic mirror descent, then the samples will actually lie around the minimizer. So this then gives us an additional tool to kind of measure the convergence speed. Since if we can measure how fast our empirical measure converges to this invariant measure, this will also give us information as to how fast our particles converge to particles that are the minimizer of our objective function. The way we can study this is using various tools from the sampling community. In particular, there is this theory called Bakri-Emery theory, which basically shows that if we can prove a certain curvature condition on our thing that's kind of inside this invariant distribution, the exponent of this invariant distribution, if we can prove a certain curvature condition, then this will actually imply that our empirical measure eta t is converging exponentially fast to our empirical invariant distribution, with the speed of this being defined as this through this curvature condition. Luckily, we can indeed prove this kind of curvature condition in particular, we can show that this holds with this kind of, our rho is essentially equal to this, where we have again our noise term, our strong convexity term, and our interaction eigenvalue of our interaction matrix. And in this way, what we can show is that we indeed have exponential convergence to the invariance measure. So our particles are converging exponentially fast to samples from this invariant distribution, which then means that in exponential time, we will be lying close around the actual minimizer of our objective function. So this is just another way of looking at the convergence speed. I just want to kind of show that studying the invariance measure, the structure of the invariance measure, and the convergence speed to this invariance measure gives you an additional toolbox for kind of understanding how fast we will actually be converging to samples from our to our optimum of our objective function. Okay, so now let's look at some numerical examples, so to see how our interacting stochastic mirror descent actually works in practice. First of all, let's consider an ill-conditioned problem. So consider that our optimization objective is to minimize this wx minus b in squared L2 norm with our x lying in some constraint set curly x, which here we take to be the unit simplex. The matrix W is then sampled in such a way that it has a high condition number, or in other words, the problem is very ill-conditioned. Intuitively, just to give an overview, what ill-conditioned means is that our gradient can get very, very high. So it's very easy to kind of overshoot our optimum and not converge close to the actual minimizer of our objective function. So what we then do, if we then compare different algorithms. So if we run just one instance of the optimization objective, so just one instance of stochastic mirror descent, if we then run 10 particles and let each of them interact, or if we run 100 particles and let each of them interact, what we see in this left picture here is that the one particle is this blue line. And we see that it only converges, well, it converges up to a certain value, but it doesn't converge any further after some point. But actually our interacting algorithms are able to converge a whole lot lower. So actually, like expected from the theoretical results, using interaction, we can converge closer to the actual optimizer. We can also see this represented in this histogram on the right, where actually we see that the particles with just one, using just one particle, are a lot more spread out than if we were to use 100 particles. So the histogram of 100 particles is a lot more centered, which again shows that using interaction, we are able to decrease the variance and converge closer to the optimum, also in a highly ill-conditioned problem. Another problem that's interesting to look at is a traffic assignment problem. So the objective in this traffic assignment problem is essentially, imagine we have this graph where the graph represents connections between each of the nodes. You can think of it as kind of like a map of the city where each node represents a certain location in the city and each edge represents whether or not we can travel between those 2 points. And the objective of this kind of traffic assignment problem is to compute given 2 nodes, so given A and B, to find the optimal path between these 2 points. So how can we fastest go from A to B? This problem can also be rewritten into our convex constraint optimization objective with a simplex constraint. So it very well fits our framework of using stochastic mirror descent to optimize it. These are the details, but I think I will kind of skip over them. But essentially what we see here is that, first of all, if we compare regular gradient descent, so the projected gradient descent that I spoke of in the beginning, and compare it to mirror descent, what we see is that gradient descent converges a whole lot slower than mirror descent. So this again relates to what I was saying in the beginning. If our optimization problem is of a sufficiently high dimensionality, which is obviously the case if we consider a very large graph, then gradient descent is super slow and mirror descent is actually a whole lot more convenient. If we then look again at stochastic mirror descent and kind of try to understand what are the variance reduction, what kind of variance reduction do we see in this traffic assignment problem? And if we again compare just running one algorithm, so the red thing stochastic mirror descent, running 10 particles, the green one, 100, the orange one, or 1,000, the blue one, what we then see is, as expected again, using more particles allows us to converge closer to the actual optimum. So our particles are a whole lot less spread out. They're a lot more concentrated around our optimum, in this case, this value here. Another thing that's interesting to look at is mini-batch optimization. So remember that at the beginning I said that another approach for minimizing the effects of the variance, so another approach for converging closer to our actual optimum, is to decrease the variance over time. In other words, this means using a larger batch size, so computing a gradient which has simply less noise. Then we're also mitigating the effect of this noise and converging closer to the optimum. So what is then interesting is to kind of compare how our algorithm using, for example, n particles compares to using a larger batch size. So if we consider, again, an optimization function of the form that I considered in the first example, where our W is this ill-conditioned matrix, but now we consider a sum over these i's. If we then sample our gradient using a subset of the data, so if our gradient is computed over this curly S, which refers to the size of our batch, so how many data points we're using to compute the gradient, then our noise is essentially included in this gradient estimate. So the smaller our batch size curly S is, the larger our noise is in the algorithm. So what we want to understand is how does increasing the batch size, so increasing the size of this curly S, compare to increasing the number of particles in our algorithm. If we look at the numerical examples and we run 4 different things. So first of all, we run a batch size, a gradient descent optimization using a batch size of 10, and we just use 1 particle. Then we run 10 particles using, again, a batch size of 10. Then we can increase the number over which we compute the gradient to 100, but just run 1 particle. Or we can use a full batch, so use all of our data to compute the gradient and then just run 1 particle. So what we want to see is what is actually more useful. Well, what we see from this plot, the left one, is that if we use just 1 particle and a relatively small batch size, this we're only able to converge up to this level, which makes sense since we have a lot of noise in our algorithm. We don't use any interaction. We don't decrease the noise in any other way. So at some point we just get stuck at a certain distance to the optimum. The size of this distance is obviously defined by how much noise we're adding into our algorithm. If, however, we then run either 10 particles using the same batch size, so the orange line, or using a full batch or the gradient computed over 100 samples, the convergence is actually the same. So what I want to say with this is that increasing our batch size 10 times, so you're computing the gradient over 10 times more data, is kind of the same in terms of convergence as increasing our particles. So using, instead of 1 particle, using 10 particles obtains the same convergence as using a larger batch size, but sticking to 1 particle. So in terms of computational cost, they're kind of comparable, and in terms of convergence speed as well. Then a more interesting problem, namely non-convex optimization. So for all of the theoretical results that I showed, we considered that our objective function f was a convex or a strongly convex function. In neural networks, obviously that's not the case, because remember this example that I showed in the very beginning, where the loss function is very often like a hugely non-convex function. Let's consider something a little bit more simple than the optimization objective in a neural network. In particular, we consider something that's called the Müller-Brown potential. It's a non-convex function with several saddle points and several local minima. So now the question is, what is the benefit of using interacting particles in a non-convex optimization problem? Well, the benefit is actually twofold. So first of all, if we forget about the noise for a second, so just consider gradient descent, no noise, and no interaction. And if we start our algorithm from a saddle point, so this orange line is a, okay, so these gray lines that you see here are saddle points. The green lines that you see here are local minima. So if we start our algorithm from a saddle point, in particular, we start here around, 0.2 in our x coordinate and 0.4 in our y coordinate, and we consider no interaction and no noise, then obviously our algorithm has no way of escaping the saddle point, since the gradient in the saddle point is also 0. So we kind of remain stuck in this saddle point. Now, the interesting thing is if we then increase our interaction strength, so we run more particles and we let them interact and we actually put more value on this interaction, so increase this interaction strength, we see that at some point our particles are actually able to escape this saddle point and converge into a local minimum. Why is this interesting? Well, essentially what happens is that interaction adds a certain amount of instability to our particles, so that our particles no longer remain stuck in this saddle point, but they actually escape it into a local minimum, something that's obviously, that could be of value in non-convex optimization, where our goal is to escape these kinds of saddle points. A more common way of escaping saddle points is using stochastic gradient descent, so using the noise, because obviously the noise also adds a certain amount of instability to our algorithm. So we're also able to escape the saddle points into local minima. But if we then consider, again, let's say 10 particles and forget about the interaction, so looking at this, these left two plots, what we see is due to the noise, starting again from this saddle point, our particles are actually converging into different values. So depending on what distance the noise is pushing them into, they are converging into different local minima. This is obviously not something that we want. So if we consider the setting, for example, of distributed optimization, where we have many, many nodes, each of them are getting certain information about the objective function that we want to optimize. In distributed optimization, we obviously want all the particles to converge to the same value. So what we can then do is we can increase our interaction strength in the following way. So if we increase it from 0 to 2, in this right plot, you see that this actually allows us to control that our particles are converging to the same value. So again, makes sense from our from the way we define our interaction algorithm and from our theoretical results, namely that interaction can kind of make sure that we are keeping this fluctuation term, which I showed a few slides back, small. So, but in non-convex optimization, obviously something that could be of interest if you want to control that all particles are converging to the same value. I briefly want to kind of mention two other applications as to why this whole setting that we are considering is actually interesting, also why it could be interesting in various applications in finance. So the first thing is kind of something that I already mentioned, which is distributed optimization. So if so something that's kind of become popular recently is this thing which is called federated learning, which essentially is just distributed optimization. But the thing that's happening there is that we are having multiple nodes in our optimization setting, and each of these nodes has only access to a certain local amount of data. So this is the case, for example, when we are having data from each of the mobile devices of many, many people, and the objective is to learn kind of a global model that exploits all of the data that's stored on these local devices, but we don't want to send this data to actually a central server. We want it to remain on these local devices. So this is the setting that's the case in distributed optimization, or what they call federated learning. Obviously, this is of benefit also because of privacy constraints. We want the data to remain stored on your local device instead of being sent to some central server. So what the objective in this case is that each of our particles have access to some objective function fi of x, and their goal is to collectively optimize this f of x, which is the sum over all of the particles. Now, the challenge here is that our particles will, on how we defined our optimization algorithm, remember that our particles are exchanging their values. But this can actually also leak certain information about the users in the system. So ideally, we don't want this. Now, what's a solution here is to actually add noise to the model. So instead of just exchanging the values, we exchange values with a certain amount of added noise, which is exactly what we considered in this interacting stochastic mirror descent. And then this noise intuitively can add a certain amount of robustness to the algorithm, which then amounts to us being less able to extract certain privacy sensitive information about the users. So this is just a very, 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 very brief overview of why our interacting stochastic mirror descent can actually be interesting in a particular application, in particular federated learning, where we want to make sure that all the data is exchanged in a safe, privacy sensitive way. That's one thing. The other thing that's also interesting is that If we are again sending data from some local device to the cloud, this data can also include lots of sensitive data, again, like I said before. And ideally, what we want to do is to make sure that data that we are sending into this centralized server, it is containing the information that we need to learn the global model, but it is kind of filtering out the data that is privacy sensitive. So this is from the paper that's mentioned here. Essentially, what we want to do is, if we look at this picture, if our goal is to simply understand whether or not a certain image contains a smile or not, we don't actually need to know the way the eyes look like. We don't need to know the skin color, etc. We are only purely interested in whether or not a smile is present. So ideally, like I said, we would like to add a certain amount of noise into our data set, such that all the irrelevant data is filtered out and we are only left with seeing the smile. The reason I'm mentioning this again is that this problem, so this kind of optimization problem of which kind of noise to add such that we can still learn a good global model, but we are filtering out all the irrelevant data. This can be formulated as a constrained convex optimization problem. So again, exactly the objective that we were considering in this work, for which we proposed interacting stochastic mirror descent. In particular, the problem looks like this, again, just very briefly, but the objective is to minimize the information between our original data X and our noisy data X hat, such that we can still obtain a relatively accurate model, so that the loss on using our data X hat is sufficiently small. So these were just two very, very brief other kinds of interesting applications, which also definitely have interesting applications in finance, where data sensitivity is also something that's hugely relevant. So that's it for the presentation. I don't know if there are any questions.
All right. Thank you very much, Anastasia, for a very nice presentation with a lot of information and detail. I saw two questions already in the chat, and please don't hesitate to ask more questions in the chat because we have some time. The first question, already three. The first question is from Chris Verzel. On slide 35, in the distributed setting you mentioned, would you run into computational overhead problems from the communication required to enforce interaction?
Yeah, that's a very good question, actually. So I didn't necessarily go into very much detail into, wait, let me go back to my interacting stochastic mirror descent. Here. I didn't actually go into very much detail into the structure of this matrix A. In particular, the only thing I kind of said is that we want our particles to be exchanging values sufficiently often to keep kind of this this lambda value that we saw in the convergence properties as high as possible. But there are certain ways in which you can choose this interaction matrix such that you are still having a sufficiently high convergence speed, so that you're not influencing the convergence to consensus, but still keep the communication cost at a minimum. So I didn't go into this, but there are ways that you can define this matrix A such that you can keep your computational cost low, but still enforce the particles to at some point reach a consensus, essentially. So yeah, that's the answer.
Colum has a question. Could you say a bit more about the trade-off between increasing N and the computational cost, and how this compares with traditional methods such as reducing the learning rate?
Yes, that's also a good question. Indeed, I think that's the main kind of thing that you need to understand well, to understand whether this interacting particle optimization can actually be of benefit in practice. If you look at what you need to obtain convergence by reducing the learning rate, if I remember correctly, I think theoretically you obtain something like an exponential convergence of the learning rate to then converge to your optimum. So your convergence is slowed down. In our case, our convergence is not necessarily slowed down, but we do need more particles. We do need to compute the optimization algorithm for more particles. So we have kind of n times the interaction cost of an individual particle. But the good thing is then we don't have to decrease our learning rate. But to understand this trade-off, I think we only did these experiments with the mini batch optimization, not necessarily yet with the learning rate. I think that's something we need to do for sure to understand the practical benefits of the algorithm. I guess the only good thing is that our algorithm is very easy to, or relatively easy to parallelize. So we can run each of these particles on a different distributed server and then kind of keep the convergence speed high by not having to decrease the learning rate and spreading the cost across different processors.
There's a question from Edouard. What's the nature of the particle? Of the partial? Are they, for example, eigenvalues of the noise? Could it be indexes of the neural network nodes? And how do you define A? And what are the starting values for Z? Could A be a precondition matrix?
Let me think where to start. If there are eigenvalues of the noises, I am not sure about this one, whether they can be indexes of the neural network nodes. I guess, I'm not sure, but maybe with this question, you're kind of referring to these papers where they use interacting particles to analyze the convergence of neural networks. And in this case, indeed, each particle refers to a parameter in the neural network or a node in the neural network. In our case, that's not really the case. It's a bit different. We basically, when I say particles, and if we would consider the problem of optimizing a neural network, what I mean is just we start out with we initialize n particles at different points in our loss surface, and then we just run the optimization algorithm for each of these particles. So there isn't necessarily a connection to the neural network nodes in the algorithm that I proposed here. How do we define Aij? Well, there are different ways to define it. It kind of refers again, I guess, to the first question. There are actually lots of interesting ways and also lots of interesting research done in how we can define this interaction matrix A in such a way that we keep the convergence speed to consensus high, but the interaction cost or the communication cost low. In our case, we for now did it very simply. We took it to be 1 over n, so basically a mean field interaction matrix. But the next step is definitely to study more interesting interactions. The starting values of Z, they depend on the problem, depending on how what we're trying to solve. But I guess the only thing that I can mention here is obviously each of the particles needs to be initialized at a different point in our loss surface. Otherwise, there is no value in it. So ideally, you would kind of have them spread out in your optimization surface. And regarding the precondition matrix, that's actually also a good question. It's not necessarily the same, but there are relations between our algorithm and kind of the preconditioning algorithms. I'm only now starting to study them, so I can't give a very detailed overview, but I think it is something that we will look into for sure, because there are, like I said, these relations with preconditioning the dynamics to obtain for faster convergence. So it's a good point.
Then there's a question from Yuying. Does the method also apply to piecewise differential but non-convex optimization problems?
Yes, but I have no theoretical guarantees for you here, because right now we've only studied F to be convex or strongly convex. Again, our next step is to extend the results to a non-convex objective function. We're working on that now, so hopefully I will have a more detailed answer there. But I guess if we look at the numerical results, well, obviously this was a differentiable function of piecewise differential, but at least in this case, we do see benefits from interaction 1 in the form of adding instability to our algorithm. So we kind of hope interaction will do 2 things. So first of all, it adds a certain amount of instability. So we kind of hope that it will allow us to converge to more stable minima. And the second thing is obviously it allows to control the effect of this noise to make sure that we are having consensus if we impose a sufficiently high interaction strength. But the theoretical results we are working on.
There is a final question from Edouard. He says, did you try to use second order methods like conjugate direction that doesn't require linear minimization to speed up the convergence?
Yes, we did. I don't know if it's convenient. We have a shorter version of this paper will be presented at this ICML workshop on beyond first order optimization methods or something like that. And there we actually also studied second order methods. Maybe if I kind of exit my screen, I can very, very briefly show you, not that a result. This is the result here. So I hope you can see it. Maybe you can't see it very well actually. Can you see it, Kees, or no?
It was better in the
okay.
Yeah, this is better. This is better. Yes.
Okay. So the reason second order methods are actually interesting is because under certain assumptions, what happens is that we are not actually able to make sure that the particles are converging and to optimality and to the same value. And so second order methods are interesting to make sure that this does happen. So this is relevant for the distributed setting. So in this plot, what you see is if we consider only the first order method, the orange line, we're at some point just stuck. We're no longer converging further to the optimum. But if we then look at this black line in which we are considering second order interacting mirror descent, we are converging way lower to our optimum. So second order is a good idea. We are trying to see if what exactly are going to be the benefits, in particular in distributed optimization. I think it will help to converge and to optimality and to consensus. But yeah, also details on that will come later, I guess.
All right. Thank you for your answers. I think you answered all the questions in the chat. So thanks again. Applause from my side. And we move on to the next speaker. And the next speaker is from our own group, Shuaiqang Liu, final year PhD student. And he will talk about deep learning for large time-step simulations of stochastic differential equations. Shuaiqang, are you there?
Yes, can you hear me?
Yes, yes, yes.
Good. Okay. So can I start?
Yes, the floor is yours. You can share your screen and
okay.
Everything is loud and clear. I will check if your full screen is visible and then
share my screen.
the green one.
Yeah, this one. Can you see it?
Yes.
Okay. Okay, so yeah, I will take this one. Full screen, okay?
Everything fine. Go ahead. The floor is yours, Shuaiqang.
Thanks. Okay, hello everyone. I am Shuaiqang Liu. So I'm working together with Le and Professor Kees Oosterlee. Today I'm going to talk about deep learning for large time-step simulations of stochastic equations. Okay, so this presentation is divided into the following sections. Firstly, I will give a brief introduction on classical
Shuaiqang, maybe switch off the video because of the bandwidth.
You mean the
your video? Otherwise, we cannot hear you very easily.
Hear me?
Yes, but the bandwidth is not so good. So if you switch off your own video, your own.
Okay, so I'll
yes.
Okay. Yeah. It's better now.
Yes, I think it's better now. Thanks.
Okay. Okay. Thank you. Okay. So yeah. So follow the in the next section, I will introduce a data-driven numerical scheme, and finally, I will show you some numerical experiments to show how accurate the proposed method. Okay. So let's get started. As we know, so stochastic differential equations are widely used to describe uncertainties in different fields like finance, physics, epidemics. But as you know, the analytical solution is not always available. So the most popular technique to solve stochastic differential equations is based on Monte Carlo simulation. In this talk, we focus on time discretization, in particular, large time step simulations. So in that case, we need accurate numerical schemes. But this highly accurate numerical schemes are difficult to develop. So recently, we know deep learning techniques have been successfully to solve PDE's partial differential equations. So the question is, can neural network help us to learn higher order numerical scheme to solve SDs? Yeah, here is a generic scalar equal SDs. So let's say, okay, the random variable yt with drift term A and a variance B. We have a Wiener process Wt, and given the initial value y0, there are two ways to define the convergence rate of discrete solutions: the strong convergence and weak convergence. Here we focused on strong convergence because a strong convergence order implies at least the same order of the weak convergence. Here's the definition of the strong convergence. Assume you have a time grid delta t, the time grid size is delta t. So that's the exact solution at the time ti given by y ti, right? So discrete approximation y hat, we have the expectation of the error hat is bounded by c times delta t, the power of beta s. The order beta s is the strong convergence order. So we will use a numerical scheme. In this slide, I show you two classical numerical schemes. As you know, we have Euler scheme. These two classical numerical scheme has and we know the strengths for these two classical numerical schemes. For in the Euler scheme, the strong convergence order is in the Milstein scheme, we use a higher order term, the zeta. Zeta is a normal distribution. So zeta squared, this high order term in the Milstein scheme, so we can achieve strong order, that's strong order 1. Yeah, so how to further improve numerical accuracy? So there are two ways, including higher order terms or reduce time step size, right? So, but these two ways also have some challenge. For example, in the case of the high order terms, you can see from this formula, if you want a term, a strong order equals, let's say 2, okay, you need 12 terms in this formula. So you can imagine how many terms if you want, let's say order 3, order 4, right? So this high order numerical schemes actually are very difficult to implement and also difficult to develop. The second way is to reduce time step. So that means you need a finer time grid, but the computational cost also grows rapidly with, let's say, more time points. Yes, also our objective is to take advantage of machine learning to derive numerical schemes for accurate large time step simulations. As I'll show you why is the feasible. So for example, if you look at the Euler scheme, actually there are two kinds of variables in this formula. So a random variable zeta is a standard normal distribution, and the coefficient alpha 0 and alpha 1. So we can see, okay, this coefficient actually are functions of model parameters and time t and delta t, right? Maybe, so our objective is using machine learning with deep neural networks to approximate this function, because this functions, always we don't have closed form for these functions in the case of high order schemes. But we need the help of with the help of the stochastic collocation method. I mean, we combine deep neural networks and the stochastic collocation method. which I will introduce in the next slides. Okay, I will spend a bit of time to introduce stochastic collocation monocolored sampler. The aim of stochastic collocation method is to invert computational expensive cumulative functions in an efficient way. So suppose you have two scalar variables, y and x. X, let's say, is a cheap distribution. Y is an expensive distribution. So their cumulative distribution functions can be connected using formula 5. When these two cumulative functions are strictly monotonic, actually, we can construct a mapping function g, small g, to map samples from distribution x to sample from distribution y. So the equation 6 actually hold in the sense of both distribution and element wise. So in other words, so that means the mapping function is a bijective function. So you have, for example, if you have a particular random sample in distribution x, you will have a particular corresponding particular sample in a distribution y. So that means element wise. So next. But as we see in this slide, actually we need to invert the cumulative CDF y, right? To construct the mapping function g. So the basic idea of stochastic collocation method is to, okay, we can approximate a function small g at some at a set of optimal collocation point. For example, let's Gaussian quadrature points. That means we can reduce the inversion. Yeah, we can reduce the number of inverting the CDF of y. If we have a collocation point, then we can write out the polynomial chaos expansion. Let's say the formula 7. In formula 7, we can say the target distribution y actually can be, okay, it's a linear function of polynomial, linear combination of a cheap distribution x. Actually, because the optimal collocation point is known, because we can, for example, if we choose Gaussian quadrature point, actually the function, the matrix A is known. That means we can use this formula, A matrix A times alpha equals y hat. We can connect the collocation point with the coefficient in the formula 7. So actually, in principle, the stochastic collocation method is a kind of polynomial, the chaos polynomial chaos approximation. So according to the theory, Cameron-Martin theory, we can know that the polynomial chaos approximation based on normal distribution can convert to any probability distributions. But in the framework of stochastic collocation method, actually we can achieve exponential converts, right? So here is a summary of the SCMC. We call SCMC the stochastic collocation Monte Carlo algorithm. Is a summary of this algorithm. So 3 steps. Step 1, we calculate the CDF fx on a set of collocation points. Then we invert the CDF y on this set of collocation points. We get a m that's triples, right? Then the step 3, we can calculate the interpolation function y bar equals j hat x bar. So we can use this simple interpolation function to map a cheap distribution to an expensive distribution. That's the basic idea of stochastic collocation method. Here I will give you a toy example. Assume you have a cheap distribution x. This is a standard normal distribution, and we have a Gaussian quadrature point x hat in the first row, right? Then our target distribution is a gamma distribution. This is more expensive than the cheap distribution x. So we can invert the cumulative function on this collocation point. So this optimal collocation point to interpolate the function g hat. Here are two figures on the left-hand side. That's this figure shows where are the where are our target optimal collocation points. Right? The second plot shows, okay, if we do interpolation, we can see the interpolation function g hat is perfectly fit the exact mapping function. So yeah, that's I hope you can get some basic feeling about stochastic collocation method. So in other words, we can do monocolor sampling in a normal distribution, then easily get a monocolor sampling in a target distribution y, right? When the target distribution y in the stochastic collocation method is a conditional distribution, actually we can derive numerical schemes for stochastic collocation, stochastic differential equations. Need to be specific what a numerical method does at the time t plus delta t is to draw a sample from this distribution, which is conditional on the previous realization yi, right? So yeah, then we can use, okay, if in the framework of stochastic collocation method, we can use this formula yeah, to draw a conditional sample y plus delta t, because we can calculate the coefficient alpha 0, alpha 1, alpha 3 if we have 3 collocation points. But for the well, in the Milstein schemes, we can write out the explicit function of this coefficient. For example, the random variable is a normal distribution, and alpha 0 is like this. Okay, alpha 1, alpha 2. We can get an explicit function for these coefficients. But I mean, actually, if you look at this coefficient, you know that those coefficients are time varying. It means this coefficient will have different values at different time points. So yeah, also of course the stochastic collocation also vary at different time points. But we can use the matrix A to connect those conditional coefficients and stochastic collocation points, because the matrix A is pre-computed, so we can calculate matrix A in advance. This matrix A is independent of time. Yeah, but I mean here we can simplify the function h hat for the coefficient for the collocation point in the case of Markov process, because we know the Markov process is a memoryless process. So this process doesn't mean this function h hat doesn't depend on time ti, only depends on time difference delta t. I mean, we will use this property in our numerical experiments. So, I mean, in this slide, we can see that actually learning the coefficient alpha is equivalent to learning the stochastic collocation point h hat. And so there are two ways. To find this coefficient. If we want to use a neural network as a regression function, the first one is to output the coefficients. If we give the model parameters into the neural network, the second one is to output the stochastic collocation point. Then we can calculate the coefficient according this formula. We prefer the second one because of the stochastic collocation points have physical meanings. That means we can understand them. They are interpretable. So we use neural network to approximation this function h hat. Then we can calculate the coefficient AI, use this formula. So that's the basic procedure. Next our aim is to train a neural network, use supervised learning to approximate the collocation point function h hat. In principle, the neural networks are powerful function approximators. So fully connected neural networks are a composite function h. So small h stands for the hidden layer functions, and the theta means the hidden parameters, including weights and bias. So I think maybe you are already familiar with this expression. In the context of supervised learning, actually we want to minimize the loss function, and if we can minimize this loss function, actually we can reduce the distance between the target function and our neural network function. Usually we imply an optimization, for example, stochastic decision algorithm to get the optimal value of these hidden parameters. But the question is, how powerful is the neural network function? Is there enough approximation capacity to represent the collocation points? According to the universal approximation theory, we know even a single hidden layer neural networks can approximate any smooth functions when the number of the neurons tends to infinity. But in addition, the depth, the number of the hidden layers also plays an important role. So the impressive power grows exponentially with the number of the hidden layers. So according to this theory, I mean, if we want to achieve a certain error, let's say epsilon hat, actually we can design the neural networks like this. So at least we need piecewise activation function. So we need at least a certain number of hidden layers and a certain number of computational costs. So then we can use this kind of neural network to achieve our desired error, epsilon hat. So in other words, an arbitrary approximation error can always be achieved with a sufficient but bounded number of hidden layers and nodes. So this theory tells us, we can train a deeper neural network to achieve our desired error. We don't need we need an unlimited number of hidden nodes, right? So the recent advances in machine learning can enable us to train very deep networks. So this technique will make neural network regression more practical. But what does it mean? What does this mean? In the context of learning the collocation point, that means we can reach any desired prediction error by designing a suitable deep neural networks. So the error from the neural network is controllable. That means we can control the error from the neural networks. So what is the error from the stochastic collocation method? Yes, we can estimate the error from the stochastic collocation method. It's epsilon m. So in this formula, that means the error epsilon m is bounded by this equation. So in other words, the error of stochastic collocation method exponentially converts to 0 when the number of stochastic collocation point grows. So that also means the error from SC method is also controllable. So we can control two errors, one from stochastic collocation method and the other one from neural networks. Assume, we can assume, if these two errors can reach 0, actually, when we combine the neural networks with stochastic collocation method, have a very good, strong convergence. if you look at this formula, so the expectation of the, let's say the sample path error is bounded by epsilon. Epsilon is a function of delta tau. I mean the delta tau is time step size is used to create training samples. So when we train the network, actually we can choose a big time step delta t in the prediction phase. So that means, okay, your strong convergence error epsilon, I mean, it's always good regardless of actual time step size if we have very small delta tau. Yeah, let me summarize the procedure of neural network method combined with stochastic collocation method. We have two phases, the offline phase and the online phase. In the offline phase, first we generate the training samples, use any classical monocolor method, but we choose a small time step delta tau. Then we can use network estimate the function h hat. Okay, this process may be computational expensive, but it can be done it can be done offline, so we don't worry about this one. After training the network, we can move to the online stage. That means we can use the already trained function h hat to calculate the collocation point at time t I plus 1. For example, we already know the previous realization yi, right, at the time ti. So we can plug these variables into our neural network function and calculate the collocation point at the time t I plus 1. When we get this collocation point, we can calculate the coefficient alpha I plus 1 using this formula. Then we will have a numerical scheme like this one. So y I plus 1 equals sum of the coefficient alpha times the random variable zeta. Then we can repeat this process until we arrive at terminal time t, big T. So then this is like a classical the classical monocolor setting, but we replace the procedure of computing the coefficients. Okay, next I will show some numerical experiments and also an application in finance. So we will price Bermuda options use this kind of numerical based monocolor method. First let's consider GBM, so geometric Brownian motion. When the drift term A the drift term A and the variance term B is a function like this. So we can have a GBM. The drift term mu and drift variable mu and the variable the variance sigma are constant in this case. So if we use mu stand scheme to solve this GBM, we can write out this formula. So we can see the coefficient are time varying. So at the different time point, we have different coefficient. But we can also use ANNSCMC method, the neural network stochastic collocation monocolor method to solve this GBM. Because we know the analytical solution of GBM, so we can, in the slide back, we can compare the strong convergence easily. So that's why we choose a GBM as our numerical experiments. This slide shows the setting of our numerical, shows the setting of our neural networks. We choose 4 hidden layers, and each hidden layer has 50 neurons. We use, activation function solve for plus. We use Glorot initialization technique. The optimizer is Adam. So the bet size is 1024. We train a network on 1700 epochs. Then we stop the training. Here's the training data set for we input drifter mu and the volatility sigma and the initial value y0. We generate those samples. We generated this on these domains. That means we can approximate the function on this domain. The output is collocation point with hat, that we have 5 collocation points. Yeah, I mean, after training, we can evaluate. Yeah, we can evaluate the performance of the trained network on the test data set. The goodness of fit. This variable is it's the R2. It's the goodness of fit. That means how much the predicted collocation point are close to ground truth. This is just one of the matrix, test matrix. So we can evaluate the performance of already trained network. If we look at these 2 plots on the left-hand side, this is the second collocation point, y hat 2. This one is the third collocation point. We can see they fit well with each other. So that means we can have a very accurate neural network to predict the collocation points. Next, we use this trained network. We call it ANSTMC method to solve GBM. So first of all, let's look at this pathwise error. So the dark line means the exact path from the GBM. The red line represents the path generated by mu-stan scheme. The blue line means the path generated by ANNSTSC method. If you look at this path, see, we can see the exact path and the ANSTMC path overlap, but the path from mu-stan scheme, we have a gap between those 2 paths. That means so ANSTMC method is much better than mu-stan scheme. So where is the Euler scheme? If we look at this plot, we can see the Euler scheme is much worse than the ANSTMC method. Here, because we choose a large time step, the time step equals 0.5. So that means next slide I will show you. If we vary the time step size, we can calculate the strong convergence at the terminal time t, big T. What does this mean? It means so we can vary time step size. We can choose different time steps, but we calculate the strong convergence at the terminal time 4. So we can calculate the average error over 1,000 samples. If you look at the mu-stan scheme, the red line, this red line, it means the strong convergence. You can see if we choose a big time step for mu-stan scheme, we have a bigger error between bigger strong convergence error. For the weaker convergence, it's a little bit better than strong convergence. We already know this, right? So for the ANSTSC method, we can see this flatter curve. That means even we choose a very big time step, we don't have a big error. We only have a small error. So see, this flat line means even we choose a big time step, we don't worry about our numerical scheme. Next slide is an application in finance. So if we want to price Bermuda options, actually we usually rely on long-staff Schwarzschild approach. This is kind of least square monocolumn method. So we can plug our ANSTMC method into the long-staff Schwarzschild approach. Then we can calculate the Bermuda options. So if we have a setting like this, so under the risk neutral method, the stock price y0 equals 1. The riskless interest rate is 0.1, and the strike price K is 1.1. We have the terminal time big T, right? We generate 100,000 sample paths to price Bermuda options. Yeah, here, let's see the price of Bermuda options. This row, so the reference value is obtained from the exact path of GBM. We also compare our method with the Mulestein scheme. So we can see this one for Mulestein scheme, the relevant error. The relevant error is so the difference between V and the reference divided by the reference value. We can calculate the relevant of error here. For Mulestein scheme, if we have 5 monitoring dates, the relative error is around 3%. But if we look at ANSCMC method, actually it's very small. It's like 0.04%. If we increase the number of monitoring dates, the error from Mulestein scheme is a little bit higher. But I mean, if we look at the ANSCMC method, we don't have a higher error, right? If we continue to increase the number of monitoring dates, let's say MB equals 20, see, we don't worry about our numeric scheme. For the second case, if we have a bigger volatility, we still have this very small error. So that means we can reduce the strong convergence error using our developed SCSC, our developed ANSCSC method. Yeah, I think, that's maybe a little bit faster. I mean, let me conclude the conclusion, conclude the presentation. First, we provide a data-driven numerical scheme to solve SDEs. But this numerical scheme can be used to carry out large time-step simulations with a small error in strong convergence. It's much accurate than classical schemes. But for the ongoing work, we will test this numerical scheme on more complicated dynamics. We also want to increase the computation speed. Here are the reference. Yeah, thanks.
Thank you very much, Shuaiqiang, for a very nice presentation. And there's ample room for discussion. Maybe I'll start off with a question.
Yeah.
If you have a non-Markovian setting, so I understand that you would need sub-simulation in Monte Carlo setting. Can you explain a bit about that?
Yes, if we have a non-Markov process, we can look at this formula. Let me show. Yeah, if we can look at the formula 8, actually we need the time ti in the regression function h hat. For non-Markov process, because non-Markov process is a memory-less process, so we don't need time ti. But for Markov process, we don't need time ti. For non-Markov process, we need time ti in this formula. So that's the difference between non-Markov process and the Markov process. So we can, that means we can also approximate this function. We just have different inputs.
Yes, and it means that you need conditional collocation points then, right?
Yeah, exactly. Yeah, we need a conditional on our previous, conditional on historical information.
Yes. There's a question from Yuying in the chat. It says, how did you decide the neural network structure? And can you give more details? It's a fully connected neural network, I suppose. Yeah.
Yeah, this is actually here. So, okay, let me explain. So we use a fully connected neural network. Actually, in the beginning, I used grid search to help me to design the configurations of neural networks. But the grid search is a very it's computational cost process. But I just do it once. So then we can tune these hub parameters. Yeah, but we don't have theoretical configuration to achieve very small errors. But you can also use this theory. Let me show you this theory to help you design and the initial constructions of the neural networks. For example, you need at least this number of hidden layers and this number of hidden parameters. Yeah, but this is, you can estimate how many layers you need, how many neurons you need.
Yes. Can you say something about the robustness of the network? Did you try different configurations, and did it always work with a layer more or a layer less, or a neuron more or a neuron less? Can you say something about that?
Yeah, in our case, if we want to increase the proximity capacity, actually we increase the number of hidden layers, increase the number of hidden parameters. Yeah, this is it's like a trial and error process. So in principle, if you have more hidden layers, you will have more powerful function approximators. That's for sure. But in order to reduce the computational cost, actually, we also needed to trade off between the approximation error and the computation cost. So yeah, this is a trial and error process. It's maybe you need to try many cases and see which one is the optimal, which one maybe is not optimal, something like this.
Okay, there's a question from Alvaro. Have you tried this scheme with other more complex models like the SABRE model or the CEV model or something like that? Can you say something about the planning in this respect?
Yes, so actually we are working on those complicated dynamics, right? So, but yeah, I would say this is a generic framework. So the only difference is we have different input for the network to predict collocation points. That's the only difference. But the dynamic, if you have a non-Markov process, actually this function h hat is becoming more complicated. If we look at this function h hat, actually if we want more complicated dynamic stochastic differential equations, we need to consider, maybe we need to increase the number of hidden layers, increase the number of hidden nodes. I think that's the only difference, because this is, we don't need to worry about this function, because you can have different inputs. You can have, so the collocation points is always there. That's the, but we are working on their process. Let's see. Maybe the results will be released soon, I think.
Yes, and Paul Kerber asks, are you thinking of the Heston model as well? There's quadratic exponential and more sophisticated methodologies for the Heston model. Would you compare with those, and what do you expect?
Yeah, that is our next step.
Yes.
That's our step.
Yes, yeah. I agree. In the SCMC paper, we also had the Heston model and the SABRE model. So there are collocation points available there. So it should be possible to generalize this to Heston and SABRE.
Yeah.
A question from Edouard. For Bermudan options in 2 words, where are the advantages coming from? And is it an improvement of Monte Carlo? And is it better, faster than finite difference methods?
Because we use Long-Staff-Schwarzschild framework, so this is least square Monte Carlo method. as I would say, Monte Carlo simulation is not faster than PDE techniques. So, but I mean, this is for high dimensional. Actually, we can use Monte Carlo simulations. But in high dimensional, it's not easy to use PDE techniques. It's like a finite difference method. I think yeah, we are working on Monte Carlo setting. So if compared to finance different method, actually it's not. I mean, I would say it's not easy to say, okay, your speed can beat finance difference method. That's right.
Yes, I would agree. Of course, in terms of supervised learning, the training stage is offline and expensive, and the testing phase is online and efficient, right? And this is really the attempt to take long time steps. There are other attempts in the literature to reduce the number of paths in Monte Carlo methods, right?
Yeah.
Papers
exactly.
by Ralph Korn and co-workers, they reduce the number of paths in the Monte Carlo simulation. And this is then aiming for strong convergence by taking large time steps.
Yeah.
All right.
Yes.
Thank you very much, Shuaiqiang. If there are no further questions in the chat, then I thank you as well for a very nice presentation.
Thank you.
And we are a little bit ahead of schedule, but I propose we move on, if you agree, Yuying, if you agree, then we continue with your presentation already right now. Would that be fine with you?
Yes, let me just actually first.
Yes. So first of all, so thank you very much for being here, Yuying. It's early in the morning in Canada. Yuying Li is professor at the Cheriton School of Computer Science at the University of Waterloo. She's very well known for optimization methodologies and already worked on machine learning, more than a decade ago, I would say, right? So really very senior in data science and financial data science. And she works on supervised learning and unsupervised learning, on anomaly detection, fraud detection, data-driven optimal decisions, computational finance, and computational optimization. She's an associate editor of several journals, and at present she's also the director of data science at the University of Waterloo. So it's a pleasure to have you here, Yuying, and you will be talking in our second keynote on asset allocation without pain, learning dynamic strategies directly from market data. So
thank you very much, Kees. Thank you.
Let's see if the screen sharing works, and then so Shuaiqiang's Shuaiqiang can maybe stop sharing the screen. Right. Shuaiqiang, can you stop sharing your screen? And then it's Yuying. So as soon as the screen sharing, yes, that works out fine. So the floor is yours, Yuying.
Yes, just give me 1 second to set it up. Okay, I have to do it again, sorry. Share it again. Oops.
Yes.
Okay, now it works. Okay.
It works perfectly. The floor is yours.
Well, thank you again, Kees, and the workshop organizers to invite me to be participating in this session. So in this presentation, I would like to talk about some recent research that have been conducted here with my colleague. So this is a joint work with a PhD student, Yuying Li, and my colleague, Peter Forsyth, both at Waterloo, and also Ray Carroll at a asset management firm in asset management firm Neuberger in Toronto. My colleague Peter always liked to say that he liked to quote Frosenberg from who is the previous managing director of Morgan Stanley. Every financial application problem is a stochastic optimal control problem. So certainly optimal control problems is an important class of financial application problems. So in this talk, I would like to talk about how we can learn optimal control of particular dynamic asset allocation strategies directly from the market data. Okay, so here's the outline of my presentation. So I will begin with introducing the mathematical formulation of the optimal dynamic asset allocation problem. And the focus of my presentation are particularly for problems that is involving many times rebalancing, long time horizon allocation problem. And I will talk about what is the traditional approach of solving this problem, what are the challenges. And most of my presentation, I will use a particular application problem that is the pension allocation problem as an illustration to the proposed framework. As well, I will talk about our empirical assessment in performance strategy based on that pension allocation problem. So then I'll move on to talk about what is the approach we propose to solve this class of problem that is different from the traditional approach. And in essence, we're going to take a direct learning approach from the market data to determine the optimal allocation problem. And so I will talk about how specifically we perform on learning, how specifically we do the learning. I will talk about what are the data that we will use to actually solve our learning problem. And we will use a non-parametric approach to augment the observation from the financial market. And then I'll talk about how we actually learn, because this is a multi-stage and optimal dynamic control problem. And we will propose to solve the problem by solving a single training optimization for all the multiple steps optimal control using a neural network. I'll talk about the advantage of solving problem in this fashion. And then particular to the specific application of pension asset allocation, I will describe different possibility of objective function that can be used to generate attractive allocation strategies. And I will talk about how objective function corresponds to reaching a constant level of wealth level at the retirement time, or actually getting a strategy to outperform a benchmark strategy that's used in industry. And so then I will present the computational results based on real market data in terms of the accuracy of the optimal strategy we can compute, and robustness, as well as the characteristics of the dynamic pension allocation strategy themselves. Then I will conclude my presentation. All right, so mathematically, basically we're looking at that today. We want to determine dynamic optimal trading strategies or allocation strategies, which rebalance at a regular interval, for example, every year, possibly for a long time horizon, let's say 30 years from now. And today's time, the future return are random. So we have a vector of M assets, and the return per each period is a random vector RTN. Okay, and in my presentation, I will also focus on the situation. We have some control, some constraints on the control. In particular, we will assume that no shorting is allowed, no leverage is allowed. Okay, and we will in the formulation, I'm going to also assume that our assessment, performance assessment of the strategy is based on the terminal wealth at the end of allocation time horizon. So then we can write mathematically this optimal dynamic control problem as I'm going to minimize some objective involve the random terminal wealth WT. Subject to my optimal control will be, here I'm looking at percentage allocation, so the optimal control will be between 0 and 1, and they will sum to 1. Okay, so this mathematical formulation, this mathematical optimal control problem, it's a difficult optimization problem. In fact, that it's in terms of optimization, I can think of it as a infinite dimension optimization problem in the sense that my optimal control at each rebalancing time itself, they are functions, and they depend on the random realization of your market scenario. So in any case, this is the framework of the problem I wanted to solve. So as I mentioned that I will use the pension investment as a particular example of such dynamic allocation problem. And indeed, this problem by itself is very important because that in North America and all over the world, it's increasingly recognized that there's a risk of a pension funding shortfall. And in North America, there is a large shift for pensions to go from defined benefits to defined contribution. And this means that individual investors as well as wealth managers, they are interested in finding high performance allocation dynamic strategy to meet the retirement goals or wealth growth objective. So in particular, you can imagine that the employee will have a yearly contribution, I will denote it by Q, into the retirement account at beginning of every year. Then we will need to have an optimal allocation strategies that depend on where the market is, depend on what is the wealth level for the next 30 years, and to try to optimally reach a retirement objective. Okay, so that's the particular application I will focus on, which the problem fits into our dynamic asset allocation problem. Okay, now in addition to the fact that we are looking for control functions at each rebalancing time, this optimization problem is also challenging in the sense that my objective function, it depends on final wealth, even if that objective function itself is simple, could be quadratic, could be piecewise quadratic, or could be some smooth function. Even when the objective function as a function of the wealth itself is smooth and convex, this optimal allocation problem is challenging in the sense that in terms of the control, the objective function is very nonlinear and non-convex. And this is really, you can easily appreciate that because we look at how our wealth is going to accumulate over time, and the more number of rebalancing time you have, your final wealth will depend on the controls at previous time period more non-linearly. So just in terms of as an optimization problem, looking at objective function, this is not an easy problem to solve because of the non-convexity and increasing non-linearity when you're looking at 30 years or 40 years of time horizon. Okay, so that's one of the challenges, but that's not all the challenging. Okay, so what we have, how are we going to solve this problem from the very beginning? What we have is a single market realization, and that's the maybe of the assets you are interested in investing. For example, the equity index, their return for the last 80, 90 years, right? So what we are given with as a problem we try to solve, we only have a single path of market return that is available to us. So this makes it difficult to approach this problem from if we're going to solve the problem in some kind of learning from data approach, because the amount of data is really, really small we have from the financial market. And this indeed is a typical characteristics of many of the financial machine learning problem if we approach this way, right? We have a very small amount of data for us to learn. And the second challenge is that, well, the problem can be actually become high dimensional, right? So you may think about, just stock and the bond, and you may think about, I would be looking at different index, different fund as choice of my assets. And if I want to beat a stochastic benchmark, I want to actually form the problem in that way, and the dimensionality of my problem also increase. And if I'm going to solve this long-term horizon, a high-dimensional problem, and there may be even additional information, as some of the research we're currently looking into. The market information could have other market variable we want to incorporate into our decision making. Then problem becomes very high dimensional, and that's also additional challenge, right? And moreover, how do we formulate an objective function, right? Our terminal wealth is a random, variable has a distribution. What kind of objective function should we actually formulate to get an attractive allocation strategy? And what about if I'm talking about the individual employee to find the optimal pension allocation trading strategy? There's tax consideration and then many other factors. So if I look at this problem, the original problem, directly, we indeed are faced many challenges, and it's a pain to solve it, right? So what's the traditional approach we have been using to solve this problem? Indeed, my colleague and I, when we were solving such orthogonal control problem, this is what we do, right? So we will say, okay, I have the market return realization observations for the last, 60 and 80, 90 years, whatever I have, depending on the particular market. So what do? We basically then say, we will assume some stochastic parametric model for the return, market return, right? We could be using jump diffusion model. We could be using regime switching model to try to do our best to model the stochasticity of the financial market, right? And so we get a parametric model, let's say a jump diffusion model or regime switching model. We do a model, we do a parameter estimation, and we get a optimal parametric model that fits into the market realization we observe. Then given this parametric stochastic model, then we try to solve the optimal control problem, right? And because our allocation problem is many period, and it's stochastic, and it's difficult to solve because I have a set of control function at every rebalancing time. And the traditional approach is, okay, I'm going to make the problem easier. I'm going to change this multi-stage, multi-step allocation optimal optimization problem into a single step optimization problem. And how do I do it? Well, I use dynamic programming principle. I will step backwards in time, one period at a time, to determine the optimal decision at every rebalancing time, right? And so if my colleague is a PDE expert, he would use dynamic programming principle and convert this multi-stage optimal control problem into a HJB equation. And then he will solve it backwards in time and then get optimal allocation strategy. Now, the issue with this approach is that we have the curse of dimensionality. When we do it in this way, we need to compute the optimal strategy at every rebalancing time for every possible market state. And we have, we have exponential blow up in terms of computational complexity. So this traditional approach, indeed this approach we have been taking for many, many years, it's difficult, it's painful to do because it requires us to make a stochastic model assumption on the financial market. And it's very unlikely we're going to have, we know how market works, we have a perfect model for it. And so we have error in our model assumption. And then we want to keep the model simple because otherwise we can't solve the stochastic control problem easily, right? And the estimation of the stochastic model itself, it's difficult. We can use maximum likelihood estimation, and suppose we do maximum likelihood estimation of a regime switching model, then that is actually a non-convex optimization problem, and when we are faced with local solution, and that's a difficult problem. Estimation problem itself, it's difficult to perform, right? And then based on this estimated stochastic model, then we solve the stochastic optimal control problem by using dynamic programming, and then we are faced with curse of dimensionality. We can't solve it more than 2 state variables, 3 state variables at most. So this is a traditional approach. It is painful and it is difficult. And so the question is there another way, right? Can we do it in a different way? Can we solve this optimal control problem more easily and robustly? So, so the specific question, so that's what's our objective. So the specific question we ask ourselves is that, okay, our starting point is a single path of market return realization. Is it possible actually for us to take a learning approach from based on the fact that we have only a single sequence observation of the financial market, right? And then given that we are trying to take a learning approach, is it possible for us to do it in a way to avoid the curse of dimensionality? And can we do it robustly? Right, that's the big thing. We're taking a learning approach. What we want is to perform well in the future. Right? Can we do it robustly? And suppose we are able to do it, how does the optimal strategy perform? How does it compare to the benchmark strategy that's currently popular in industry? Right? And now, if our goal is trying to beat the industry implementation, is there a way for us to actually optimally beat a benchmark from the industry? So those are the questions we have focused on, and that's my presentation will address some of those, most of those issues. Okay, so first of all, if we want to take a learning approach to determine the optimal allocation problem, where does data come from? How are we going to have the data, right? We have only a single realization of the market the assets return, right? So this is all we have, a single realization of, let's say, monthly return from equity market in the last 50 years or 90 years, right? So how do we come up with data that allow us to get to learn from the market what kind of data can we possibly come up with, and not going to the traditional approach of stochastic model estimation. So what we end up with is to use the stationary block resampling approach, which essentially generates more data path from this single return observation. So how does this approach work? So this is basically a block resampling approach. We will, based on this single market return observation, will randomly sample blocks of random size starting from the random location. Okay, and the size of the block, we will assume that it follows a distribution, okay, a geometric distribution specifically. And for the geometric distribution, we will specify a average block size, right? And I will say more about that as we go on. So then we concatenate all those blocks of different size, random size, put them together to generate a data path, return path, which is corresponds to our investment time horizon. Now the assumption here in order to do this is that we're going to assume that our sequence of market observation is actually circular in a sense that, in other words, after you reach in the last observation, you will go from the beginning to continue sample return, right? So this is the block resampling technique that has been proposed, has been used in financial time series in other contexts. Okay, so this is how we're going to generate our data using block resampling to come up with many more paths of market scenarios, right? So, okay. So, okay, we're going to use the block resampling to generate data, generate training data to learn our optimal strategy, right? So, there's some arguments that supporting that to learn the strategy using this technique is reasonable. Well, essentially what we're doing is that, okay, we think about, we have this one path of market return realization. So our market scenario, that's our augmented market scenario, essentially you can think of it as, I have market running session of random lengths and randomly permuted and concatenated them together. So in some way it is come from the market and different lengths of time period. And also, so there's some, I guess, rationale one would think this is a reasonable approach. Well, so, okay, that's fine. So that's our approach to generate our data to train our optimal allocation strategy. But what about testing data? We're doing machine learning approach, a learning approach to determine our allocation strategy. We have to make sure our strategy really perform out of sample, out of the training data set, right? So the question is, how do we generate testing data? Well, in typical machine learning, the assumption is that the training data and the testing data, they are samples from the same distribution, right? We just require our testing data have not appeared in our training data set. Our testing data instance are out of the training data set. So it's out of sample of training, but they come from the same distribution, right? So that's how we typically handle the training and testing in machine learning, okay? Now, so here we start from a sequence of market return scenario, that's observation. Now we did the block resampling, come up with 10,000, 100,000 of the market scenario corresponding to my investment horizon. We specify some expected block size to do this, okay? So how do I come up with testing data set? Well, if we say the expected block size, we use the same block resampling technique to generate testing data set. If we assume that expected block size is the same as the training data set, then our argument is that essentially you are performing out of sample test. So if you use the same expected block size as your training data generation, you are performing out of sample test. And I'll give you some mathematical rationale to support that. Now, suppose I can actually, in this using this technique, I can even generate more stringent test, if you like. And when I use a different expected block size to generate to block sample to generate my testing data set, then the distribution of my testing data set is actually different from my training data set. And so I am, in that sense, I'm actually performing out of sample distribution. No, I'm performing out of distribution test. And so that's something we will do as well. And then one might be still concerned because while you're doing your training and testing based on a single pass of a return observation from 1926 to 2015. I mean, your training and testing still come block sample of this whole thing. And are you somehow look ahead and is that reasonable? Are you really testing it? So then one can do further say, all right, I can really split my historical market observation into non-overlapping segments and generate training data from one segment and testing block sample from a different segments. And in that case, then really it's really different, and then I think it's hard to criticize that. So we actually perform all those different kinds of tests, right? And furthermore, I mean, one could, because we've been doing computational finance for so long, we can also we know how to estimate the parametric model. We can also do parametric model estimation just as additional testing, sanity checking, and generate scenarios from our stochastic parametric model for additional assessment if we still not so sure if the whole thing really works in a robust fashion. All right, so we actually in our computation we will perform all of that. Okay, so what I want to just kind of provide some kind of support that this framework we are conducting in learning and training is mathematically sound, right? So what I wanted to trying to answer, the question I'm trying to answer is that when we use block resampling, it actually doesn't lead to a solid out of sample testing. And so what is this theorem here we're trying to say? So essentially what this theorem says, okay, if I have a n total number of observation, my market realization, I'm going to do block resampling of this market realization single path. I'm going to do block sampling from this observation. Suppose I want to generate 2 paths of n data return, n data points, right? So, and path 1 is generated using expected block size of B1 hat, and path 2 is generated using the expected block size of B2. Then the probability of these 2 paths being identical is given by this expression here. Well, this looks very complicated. What is the upshot of that? Okay, so here's basically a sort of a numerical example to give us some comfort or assurance that supporting my statement that this technique does need to sound training and testing. Okay, so if I say I have 19 years of return observation, monthly return observation from the market, I need 30 years of monthly return to look at my investment horizon. If I use the expected block size of 2 years for training for 2 paths, sampled from 2 paths with the same expected block size, and if I have a training set of 100 return paths and testing set of 10,000 returning paths, and then the probability there exists a training path and testing path being actually equal is less than 10 to the power minus 29. So this basically kind of assure us, yeah, this framework is a reasonable approach for us to answer the question of how do we generate testing data using the block resampling. Okay, so all right, so that's how I'm going to generate data for my learning approach for the optimal allocation problem. Okay, now let me move on to talk about how do we solve the learning problem. Remember, our original stochastic dynamic optimal control problem is a multi-stage optimal control problem, right? And we don't want to use dynamic programming principle to convert this problem into a sequence of optimization problem by solving backwards in time, because that leads to curse of dimensionality. So what we want is that we want to see if we can actually solve the optimal control problem, the original optimal control problem, directly in a single optimization. Okay, suppose I already have my many market scenario that come from my block resampling. So I have a, let's say L or 10,000, 100,000 of return scenario, market scenario. That's given to me by block resampling. Okay, corresponds to my original optimal allocation problem. Then what I have is this scenario optimization problem, right? So I have control at every rebalancing time corresponds to different scenario, every scenario, and subject to the constraint that I have to look at percentage allocation. It's a constraint between 0 and 1. They have to sum to 1. Okay, and then I have a different, I have many scenarios of the terminal wealth based on my calculation. Okay, so the original infinite dimensional stochastic control problem, when we use the training data set, it becomes this finite dimensional scenario, a finite dimensional scenario optimization problem. Well, we can try to solve this, but this is going to be hard because the number of optimization variable will be proportional to number of assets, number of rebalancing time, and the number of scenario I have. So this is a huge optimization problem, right? So yeah, and in addition, I solve this scenario optimization problem. I'm going to apply it to in practice to have an allocation strategy. Well, this only gives me the optimal control corresponds to the scenario. But what I need is really a optimal control model for tell me at every rebalancing time how do I allocate my strategy. So this is it's still not easy to deal with the scenario optimization. Even though it's finite dimensional, it's still hard to for us to work out. Okay, so what do I do? Of course, everything. Well, let's do a machine learning approach, right? Okay, what we want is the optimal control at all those unrebalancing time, right? So the idea we're going to do, we apply is that I'm going to assume the optimal control is a function of some features, okay? And so the optimal control will be a function of feature at a particular rebalancing time, right? The feature or the state variable for my optimal control will be in this pension allocation problem could be the wealth of my strategy at this time point, and as well as how much time left to go. Or could it be other market variables like realized volatility or volatility index or whatnot you can come up with, or could be trading signal from moving average and so forth, right? So the main idea is that I'm going to represent the optimal control for every rebalancing time using a single control function, where the feature will reflect market the state variable for my control, as well as how much where I am, how much time is left, right? So if I do this representation, then my control function will be somewhat parameterized by a set of parameters like the weights of neural network, right? And then my scenario optimization problem now becomes this. I have my objective function depends on the final wealth, terminal wealth. I have the control, and then I'm determining this non-parametric neural network, which will give me the control I need for every rebalancing time. And then unknown of my optimization problem is the weights of neural network, or the parameter of my control function. So I'm making progress, right? Instead of my scenario optimization problem involving a lot, number of decision variable depends on number of scenario, rebalancing time, assets, and so forth. Now my optimization decision variable for my optimization is a parameter of my neural network. It's the parameter of my control function, which I will model it unparametrically. So that's good. I hopefully I have reduced the dimension of my optimization problem, but I still have a other issue because my optimization problem is controlled, right? My control is still for every scenario at every rebalancing time, right? So I still have order m times n times l number of constraints, and solving such optimization problem is just as hard as when you have the number of decision variable being that large. So that still doesn't work. So what do I do? Well, okay, so we're going to use a neural network to represent optimal control. I'm going to handle the constraints in some suitable fashion on next slide. And it turns out that our optimal control for the dynamic allocation problem, at least for the pension allocation problem, and perhaps can be generalized to many different problem contexts, a very simple neural network is sufficient, okay? And for the pension allocation problem, what are we going to use? What do we end up using? It's just this baby neural network. It cannot be simpler. I have features. Think about the wealth I have so far at this time, at the rebalancing time, and how much time to go. Those are my two input features. I have one hidden layer. It's just 3 hidden variables. It cannot be smaller. And then my output is P1 and P2 tell me the percentage allocation in stock and bond, for example. Right? It's a very simple neural network. And my optimization problem in terms of number of optimization variable is just number of those arrows connecting all of them. It's just a number of weights, right? All right, so that's my neural network control model. Okay, what do I do about the constraints? How do you handle this large number of constraints? Well, it turns out that we can actually, at least in this case, handle it fairly easily. What we do is we choose the activation function for the output layer carefully. Yeah, if we just use logistic sigmoid activation function, and so the output function is a function of the output of neural network is a function, this sigmoid function of the hidden layer variable, right, in this way. So we automatically satisfy the bound constraint between 0 and 1 and sum to 1 constraint, all right? So the input feature, as I meant to the input for the hidden layer, as I mentioned, is wealth level at rebalancing time and time to go, and we use a simple activation function that is written here as well. So in other words, we have a simple neural network model for our control, and by choosing activation function carefully, we were able to actually change the problem into a unconstrained optimization problem, right? So, okay, now my training optimization problem then is basically this finite dimension optimization problem, right? My objective function depends on the wealth. The wealth is calculated explicitly by this formula from the feature variable hidden layer weights, and the weight of neural network. And so I have an unconstrained optimization to train my optimal control. And the number of weights in this case is very, very small, right? It's 2 times 3, whatever. This is right here, right? Number of features, number of hidden nodes, and number of assets. Right? It's a very small optimization problem in terms of the decision variable, right? So yeah, so by using this approach, right, we actually simplify the problem significantly. The original scenario optimization problem has constraint, and number of variables is proportional to, is right here, order mn times l, proportional number of scenarios, and number of constraints is also same magnitude. And then my neural network training optimization problem in terms of number of variables is very small, right? This is a number of variables of far, far smaller than scenario optimization problem. And in terms of if I solve this small optimization problem, right, I will need to evaluate the objective function compute the gradient and compute the hashing of objective function if I want to do that, and which actually in this computation we do because the dimension of problem, because the neural network is so simple, right? So in terms of gradient and hashing calculation, second order derivative calculation, it does scale linearly with number of scenarios, right? It depends on neural network structure, quadratically if you're going to use the hashing, right? So in our computation, because what we have is like a problem, our learning problem is so small in terms of optimization variable, we actually use second order method to solve it. And the reason we do this, well, I mean, you can solve it using stochastic gradient or first order method, but the reason we choose this, there are a couple of reasons. One is that the method is more robust because it's second order method, and furthermore, there's no issue of choosing the learning rate, right? I always find that the stochastic gradient, how do you choose learning rate? You know, it depends on what you choose. Then you don't. So the second order method is feasible in this financial stochastic optical control problem context, and why not? We have a way to formulate the problem, we can solve it, right? So that is what we're going to do. We use actually a trust region method, second order method to solve it. And when the problem becomes larger, I mean, it depends on the context, how you're doing it. I mean, stochastic gradient is a possibility, and some of my students have been using it. One of the tricky issues is the choice of the learning rate, which it's challenging if it goes to first order method. In any case, so our training optimization problem is easier, less painful, hopefully, to solve it. And all right, so that's my learning problem. Okay, so let me move on to the next component of a presentation. That is, okay, what objective function should I choose? That, of course, is problem dependent. And if I'm looking at the pension allocation problem, right, a first objective function that I can think of is, well, when I retire, I want to have $2 million or $3 million, depending on how you're comfortable living, comfortableness, right? So I can say, all right, I really want at the end of the investment horizon, I want to a wealth level W star. So I can specify a wealth target. And then a reasonable objective function is to minimize expected quadratic shortfall. I want to reach that wealth level as best as I can. I want to, and I minimize the quadratic shortfall, and that will make me focus on really not to fall short. That's essentially the quadratic shortfall would bring you. And it turns out if you use this quadratic shortfall objective, the strategy is also actually, if you solve it, use this objective, it corresponds to mean variance optimization problem with a fixed risk version parameter as well. I don't have to go there for this presentation. All right, so okay, so that is the first objective function we can consider in the context of pension allocation problem. I want, when I retire, I want to do my best for my strategy to reach that wealth level. All right, so okay. All right, so sure, we will use that objective function, okay? Then how do I assess if the resulting optimal strategy really is attractive? Well, one way for me to do this assessment is compared to benchmark in industry, right? So one of the very popular allocation strategy in wealth management, in pension fund management is a constant proportion allocation, right? So we're going to use this couch potato constant allocation as a benchmark for my assessment, right? So then the immediately, okay, it says, well, if you really want to beat the benchmark, then why don't you actually use your optimization and mathematics and computation to do it, right? So then the next question is, okay, how do I actually optimally beat a benchmark? 50%, 50% allocation strategy. What kind of optimization problem can we formulate? All right, so we want to also consider optimal strategy corresponds to beat the benchmark. And the objective function we end up choose is this asymmetric objective function. Let me try to explain what is this objective function. Okay, so we basically, we want to beat the benchmark. So we elevate slightly our benchmark terminal wealth. So you can think of this exponential, this continuous compounding kind of growth rate. We call it a spread of S, right? To elevate my terminal wealth. And then what I do is I'm going to minimize my quadratic shortfall of the benchmark, right? But I'm also going to maximize of my outperformance of the benchmark. But I don't do it symmetrically. I'm going to have a quadratic shortfall and a linear outperformance. And we choose this because really, I mean, our strategy will generate a terminal wealth distribution, right? And it's difficult to describe what is the attractive strategy by a single objective function, right? And so objective function really, the objective function is doing is really trying to somehow formulate or trying to characterize the distribution of the terminal wealth we would like to have. And so basically, and that is to shape your distribution using objective function, that is a hard problem by itself. But what we did is basically saying we like the risk, we don't like the risk more than we like the outperformance, and we will end up with the stochastic benchmark outperformance objective, right? And when we look at this stochastic target outperforming of my optimal control problem, excuse me, then I just want to point out that the dimension of the problem increase, because now the wealth of my benchmark strategy at rebalancing time become a state variable for my optimal control. So the dimension of problem also increase, as I mentioned before. All right, so that's a different objective, and those are the two objective functions we're going to use to hopefully determine a optimal allocation strategy that is attractive and perform well. Okay, so this is this concludes my sort of mathematical description or my modeling and the computation aspect of the approach, right? So what I would want to move into is talk about how well does this work? Those objective function, those computational framework, and those data augmentation, do they work, right? Will they perform well in practice? So we do this assessment. We look at US historical market data from 1926 to 2015 in this presentation. That's the data we have, and from CRISP. And so in my presentation, I'm going to consider the following allocation optimal control problem. I'm going to consider two asset allocation, which involve cap-weighted CRISP index and a 3-month treasury bill. And I'm going to consider different two asset allocation just to as a different performance assessment of using equal weighted index and 10-year treasury. And we will also consider 3 asset allocation problem involve one of the index, 3 months, and 10-year treasury bills and treasuries. And of course, we will also consider beating the benchmark problem as well. Okay, so in the computational results, we use the bootstrap block resampling of the market data observation to generate our training data as well as our testing data. I'm going to also consider the situation where the data comes from a parametric model, specifically jump diffusion model assumption, and where we actually estimated the optimally, the best possibly, the jump diffusion model that described the market, same market scenario. And the reason we do this is because I'm going to use this experiment to show the accuracy of our proposed framework in learn the optimal strategy. Okay, all right, so those are the data. Okay. All right, so the first results here is basically a accuracy assessment against the ground truth. So when we started this research at the beginning, I was doing optimization, machine learning. Peter, my colleague Peter, he's doing HGB equation. He said, there's no way you can use a machine learning approach to learn the optimal control strategy in this setting. And so I said, well, try me. And so, okay, I said, okay, I'm going to do this. And then I'm going to just use 10,000 scenario from simulation of the jump diffusion model. I will learn the optimal strategy. I'm going to compare to the corresponding optimal solution that's computed from solving HGB equation, right? So this table basically is a comparison to show that actually with our very simple neural network, we are able to get very accurate solution when we compare to the true solution, the grounded truth, right? So the optimal, the neural network learned strategy. So we learned from 10,000 scenario. This performance, the statistics right here is collected by using 160,000 Monte Carlo simulation of the same parametric model. So you can think of my test model if you want. So this is a 2 asset allocation problem. We use the cap-weighted index, right? So the key thing is here I want to point out is that if we compare the neural network strategy with the grounded truth strategy, you see the expected wealth here is exactly the same. Actually, we choose the wealth target so that the expected wealth from the two strategy actually will be the same, which is the same as a constant proportion average wealth. So we put them all the same. We can do this by just changing our target. I think this, I might have a typo here. The target is different from SIM05. It's a bit higher. So the all strategy will have the same expected wealth, okay? Now let me compare the neural network strategy and the grounded truth in terms of standard deviation. They are very close, and the median of the terminal wealth is very close, and the probability of falling short on a few wealth level, 500, 600, they are very close. Right? They are essentially, it's sufficiently close to the exact solution. The difference comes from that the strategy is computed using 10,000 simulations of the same stochastic model, right? All right, so that's first one thing is the accuracy assessment. We say indeed compared to the exact solution, numerical exact solution, and the learned strategy perform just very similarly. Now, if we compare this to constant proportion strategy, where we allocate 50% to equity index and 50% to bound, we see that while the optimal strategy from stochastic optimal strategy has much smaller standard deviation of terminal wealth, much higher median wealth, and the probability of falling short of the wealth level 500, 600, and the wealth target, the optimal strategy, it's just significantly better, right? So that's basically the first, the results I would like to describe. All right, so that table here basically compare strategy based on a few statistics, right? A few quantile, right? So what about if I look at, I want to have better picture, more complete picture. Well, to do that, we can look at CDF, right? So here, this plot here, we basically plot the probability of terminal wealth less than a wealth level. So the horizontal axis is the wealth level, and the vertical axis is probability of falling short on that wealth level. And so here are the what I want to draw your attention to. So the green CDF here corresponds to optimal control, computed from neural network learning approach. The red one corresponds to the grounded truth, computed from HGB equation. And you see these two CDF nearly coincide, right? There is bit of difference. That's because, as I said, neural net control is learned from 10,000 scenario of the stochastic model, right? And so that's first comforting observation. Now we compare it to the constant proportion strategy, the blue curve here, CDF of a constant proportion strategy. And we see that, so because our objective function is trying to reach the wealth level, which is somewhere 700 something here, right? So we see that, of course, our objective function ignores wealth above it. I don't try to achieve there, right? I want to achieve this wealth level as much as possible. And it's able to do that, right? So relative to the blue line of constant proportion CDF, the optimal strategy is lower in this entire segment of the wealth. The shortfall of the wealth below that, terminal wealth below this wealth level in this segment is significantly smaller for the optimal control solution compared to the 50% strategy. And of course, on the very extreme left tail, there is a small probability of the constant proportion strategy actually is slightly better, right? But this is what objective function, quadratic objective shortfall can achieve, and indeed it does a pretty good job for a large horizon of a wealth level achieve above that. Okay, so the left plot is for cap-weighted to asset allocation. The right plot is similar, except it's for equal weighted and 10-year treasury to asset allocation. So the picture is roughly, it's qualitatively similar. Okay, all right, so that's essentially the comparison in the two asset case against the ground truth and constant proportion strategy in different perspective of a few statistics and the entire CDF. Okay, all right, so what about the robustness of the strategy? As I mentioned, we perform both out of sample test as well as out of distribution test for the optimal strategy. So this table basically shows that, so we learned optimal strategy using an expected block size of a half year to generate our training data. And then we will, here, the first top panel here, report then the performance of our training with the expected block size of half a year, right? And compared to the constant proportion strategy. Oops, this is a 3 asset case. I had a table for 2 asset case before, but I think I deleted it. Okay, so this is basically a robust test results for the 3 assets case. Okay, we have a cap-weighted index, 3 months treasury bill, 10-year treasury. Okay, the first sub-panel here is the training performance with the expected block size of half year. Okay, then the next panel here, reporting out of distribution test results of expected block size of 1 year. The testing data set is generated with different block size. And you can see that, first of all, the optimal strategy is performing better than the constant proportion strategy, which is 60%, 10%, 30% allocation, I should say. And then we have out of distribution tests for different block size, 2 year, 5 year, 6 year, and 10 year. And the important point I want to make is that, first of all, across different out of distribution tests, the comparison between the 2 strategies are qualitatively similar. So, so that's a robustness test for the 3 assets case. Okay, so I have a few more computational results slides. So now I move on to talk about optimal strategy that's determined by formulated problem to really optimally beat the stochastic target. Okay, so I'm going to use 50% as my benchmark to beat. I'm going to put this elevated target to be slightly higher, basically 1% spread yearly, right? I'm going to solve the stochastic target optimal strategy training problem using training data with expected block size of half year. And I'll also do out of sample testing using the same expected block size. Okay, so here the plot is a histogram, different way of looking at distribution of the terminal wealth. The blue one comes from the optimal neural network strategy, and this pinkish one is the distribution of the wealth from 50% allocation. Okay, this is training on the left histogram, and on the right is out of sample testing histogram performance. Okay, so what I want to point out is that, well, our optimal target outperforming strategy has a terminal wealth significantly more right skewed. So because we are trying to beat the market, there's a higher probability, the right tail, higher probability of achieving higher wealth. And so then one would imagine that, well, you probably take more risky strategy, then you're going to give a lot on the left tail. But if you look at the left tail here, you see that there's only a slight underperformance over the benchmark strategy in the probability of those very of the extreme wealth level, right? So I think overall, from the whole entire distribution perspective, the optimal strategy does seem to be much more attractive on that benchmark strategy. And another point I want to make is that the testing histogram looks just almost the same as the training histogram. This is out of sample testing, right? And we have plotted out of distribution testing using different block size, and in terms of the distribution comparison between the two, it's qualitatively similar. So in the paper, we'll have more plots. All right, so this is one picture of our optimal stochastic outperforming strategy. So what is this strategy? What it's doing? What does the strategy look like? So here the plot here is trying to convey some sense of what the strategy look like. So this is the vertical axis show the percentage allocation to the risky asset. And in this case, I think it's the CAP index, right? So, and the horizontal axis is time, right? It's 30-year time horizon. Okay, so what this model gave me, what this plot is trying to show is that we show the average allocation in risk asset allocation over time, right? So this is the mean allocation, and this green line is the mean allocation. And what we can observe is that the allocation starts from initially very risk taking, and over time you gradually become taking less risk. And that's the mean, and this is the median allocation in the risky asset. That red line is median allocation. And we also plot the 55th percentile and 95th percentile in the risky asset allocation, and they all tend to be decreasing over time when you're taking less risk as you move towards your retirement time, right? And moreover, this 5% allocation seems to decrease more quickly over time. Okay, so that gives me some idea of what this strategy look like. Okay, so I'm going to have two more pictures. So remember, we generate training data from historical past by block resampling, right? Then we generate many scenarios using the block resampling, right? So the question is, how does this optimal strategy perform on the historical past itself? And now, based on the mathematical analysis I showed before, well, actually the historical past itself is not in the training set, right? The probability is in there, it's very small. And indeed here, we plotted that the black path is the historical path of the wealth for the correspond to constant proportion allocation. The blue path would be the closest path in my training set to the historical path. And the closest is being measured by Euclidean distance of the different time points in the investment horizon. So indeed, the training path, the historical path is not in the training set. And this is what the closest path look like in relation to the historical path, right? So I want to look at in the historical path itself, right? Suppose the market going next 30 years really just repeats the historical path again. What would the strategy look like, right? So here, this plot basically tells me what the strategy look like, how it will perform. So first of all, on the vertical axis on the left, it's the wealth. This is for, I guess I should mention before, our computational setting is a cash injection of $10 each year at the beginning of each year, right? So here's basically on the historical path, constant proportion is the red wealth path for the optimal strategy. Oh, no, sorry. Okay, let me start again. The red path is the performance of the wealth. It's the wealth of the constant proportion strategy. The blue path is the wealth of optimal stochastic outperforming strategy. The black curve, its vertical axis is on the right. It shows the allocation to the risky assets. Okay, so what's the point I want to make here? Well, on the historical path, the optimal strategy is turned out to be always above the benchmark strategy in wealth level, right? So that's one point I want to make. And then if I look at the allocation strategy on this particular path, you can see that it starts with around 86%, and then it went way down, okay? And so basically, when the wealth level market performed well, wealth becomes really high, the risky asset allocation went way down. And when the wealth went down, asset allocation goes up. So essentially this picture here shows two things. One is that optimal benchmark strategy is performing well on this particular out of sample historical path. Secondly, the strategy is contrary strategy. When the market will outperform, it goes down. When it goes down, it goes up. And when you get close to the investment horizon, it de-risk, the allocation becomes much smaller. All right, so that is the behavior of the strategy. I think I've touched upon all the points I wanted to make. So in summary, basically in this research, we consider a framework to look at optimal allocation problem, particularly in the context of long-time horizon allocation. And what we want to be able to do is to obtain this optimal strategy with more ease, more easily, and ensure the strategy actually perform well in practice as well. And this problem is by no means easy. It's difficult both from modeling perspective and the computational perspective. And the way we approach this problem is by using a learning direct from the data approach, not making any assumptions. And in particular, we augment market data single return path using block resampling technique. And we look at this learning framework in terms of training data generation and testing data generation. And we provide some kind of mathematical assurance in the sense that using this approach, we are indeed performing out of sample testing and out of distribution testing as well. Right? And we also look at the performance of the strategy, look at a particular historical past to show that indeed the strategy performs well. So in addition to the modeling aspects of data augmentation, we also look at how to solve the optimal control problem, and which is a difficult problem. And the way we approach it is basically using a learning, non-parametrical learning approach to determine the optimal control problem strategy directly by solving a single optimization problem. And the way we do this is by representing the control at every rebalancing time with a single control function, and the control function is a function of state variable at rebalancing time and time to go. And we demonstrate that this computation, first of all, is able to achieve good accuracy because we compare to when it's low dimensional case, 2-axis case, we compare to the ground truth. We look at the different statistics and look at the CDF to say that indeed two strategy looks very much the same, and assure us the accuracy can be achieved. And we also talk about the computationally, it's much more efficiently to solve the problem in this proposed fashion, right? And we designed objective function for different in the pension retirement allocation problem with different kind of consideration to design the objective function to achieve that objective, right? One is to try to reach a wealth target at retirement with a minimum probability of shortfalling. And then secondly, if I'm going to persuade industry that this is a good strategy, we can try to actually optimally beat the benchmark by formulate appropriate objective function and formulate a learning problem. And based on historical market data, we show that indeed the optimal strategy obtained in this framework consistently outperform constant proportion benchmark strategy, and robust testing looks good. And also the optimal strategy both in the constant wealth level target case and stochastic target case is essentially a contrarian strategy. When market goes up, it allocates less risky assets and reverse. And moreover, the allocation strategy decrease over time. As you get close to retirement age, you are exposed less in risky assets. And we believe that this framework of solving the optimal control problem, decision problem, trading problem can be applied to many different financial decision problem. And we're currently working on looking at what happens if we have to consider personal tax, and also what about we have additional thing to consider, the market signal, the factor, and so forth. With that, I hope I have not, hope my timing is okay, and I'm ready to answer any questions.
Thank you very much, Yuying, for this nice overview and this nice and detailed presentation. There have been several questions on the chat, and there's a lively discussion with questions and already intermediate answers. So I see a first question was from Shashi. He said, are we assuming for bootstrapping that the return process is stationary? For instance, I feel volatility clustering in the bootstrapped path might not hold.
Yes, so that's a very interesting question, right? So this is a block bootstrapping. And that is the reason this is the block bootstrapping is used. It's in recognition that there could be serial correlation in the time series. So if you choose the block size to be very, very small, like just 1 month, right? You essentially are saying, I'm going to generate that, ignore any serial correlation. So by varying the expected block size, you will be able to capture some serial correlation. Does that answer the question? I think that's essentially what he's asking. So we're not assuming this is non-parametric way of sampling, of generating data from time series. It will be able to capture some degree of serial correlation. But of course, one issue is how do you choose the expected block size appropriately that is actually consistent with your degree of serial correlation, if you like, of historical past, right? So that is a tricky question, but what we've done here is basically, so at least in the context of this pension allocation, we've done different block size, and of course, when you do different block size, distribution changes in the sense that the serial correlation degree of serial correlation captures changes, right? But what we want to emphasize there is robustness, and in particular, with the perspective of a relative comparison between constant benchmark strategy as to the optimal strategy. I hope that answers that question.
Yes. I see in the chat there's answers your question, he says. Paul Kerber, you want to ask it your question yourself, Paul? Because there are several questions.
Should I talk or?
Yes, yeah, go ahead, yes.
It's a bit related to this volatility clustering question. So if you patch the blocks, don't you have some artifact where it goes from one regime to the other? If it's taken from time periods where there was a different volatility regime, or, I mean, doesn't it make some artifacts when you patch the blocks together?
Yeah, it indeed. I mean, the thing is, you start with a single path observation, right? And we have to come up with a reasonable market scenario to determine optimal allocation strategy by considering everything that is reasonable. Now, the block resampling technique is essentially a way of a non-parametrically generated market scenario, but it requires the choice of the expected block size. And I agree that if you choose differently, you can destroy or you are not able to capture some of the effect in volatility clustering. And so then in some way, then the decision becomes, how do you choose the expected block size? But I think that is an important question, and I don't think I have all the answer to that. And I think it's a question actually worth to think about in further research. But what I've shown that is in this context of a long-term horizon allocation problem, right? It seems to be that expected block size choice, it's not as problematic in the sense that if we choose 1 year, 2 year, the strategy does not, the optimal strategy does not change significantly. So that's the degree I can answer your question, yeah.
Thank you. And Paul, there was another question from your side, so feel free to ask that one as well.
I was wondering how relevant very old data is. You're talking about the 1920s, or
yeah,
because I mean the markets were very different then.
Right. So that's a very good question. Okay, so we have a single path, right? And we are trying to determine optimal allocation strategy going next 30 years forward, right? So the question is, how do we describe or represent that randomness into the future? The block resampling technique, my argument is that it's essentially look at what has happened in the market in the last 80 years, whatever. And it is basically that I take a random length of market running session, right? And randomly concatenate them together. And I've considered all different kinds of scenario. So that becomes, so of course, the optimal strategy is not determined based on a single path, right? It's not, the optimization problem is not based on a single path. It's based on all the different scenarios generated in the sense of I can have a historical market session running at different lengths of time, regime, different time, and different, starting from different point, different lengths. So that's so I'm training a strategy by consider essentially in some way all the possible scenario I can come up with based on that single path, right? But the issue really is then the expected block size, I still have to determine. So your question about, are you determining the strategy based on single pass? My answer is not really, right? My training data set has 10,000 scenarios, come from random permutation, random size of a session of the historical market. So and indeed, you will see in my training data set, if you plot it, you'll see scenarios come from all different way. So you can have very different scenarios. So it's not based on a single historical path. It's not just a single historical path, but rather it's considered possible scenario based on this observation. What is a reasonable way of coming up with the scenario?
All right. Martin asks, did you compare with the optimal constant allocation? In the historical comparison, the neural network might outperform because it takes more risk.
Sorry, so compared to, I'm not so sure if I get the question right. You mean the constant proportion?
With the optimal constant allocation?
Oh, you mean optimal? Yeah, we actually did that. The optimal constant strategy doesn't perform very differently. It's deterministic, right? So it's basically, you are saying the allocation percentage is determined, the constant is determined by solve-sum optimization. We actually did that, but the performance of that strategy is not, it's not very different from a reasonable constant proportion strategy. So we did consider that. I don't have the plot here, yeah, but that does not change the comparison between a fixed proportion, constant proportion strategy with the optimal strategy.
All right. There's a question from Edouard. Does the wealth level depend on inflation? If the benchmark strategy just produce a much higher wealth than the target value, it will underperform, will it not?
Yes. That is a very good question. So if you bring inflation into the picture, you have another random factor, right? So we are currently actually looking at this pension allocation problem under tax, and in which we actually consider the inflation factors in there as well. So those are right. There are many additional things one could consider putting into this framework to answer to get to the strategy. So I think the main point of this research is really to show that yeah, we can come up with different way of looking at this optimal control problem. And we can get a good, accurate result if, in terms of solution approach, we can solve high-dimensional problem. But depending on how much factor you take into consideration, this framework will allow you to address many of those issues, and those are important. Yeah.
And then he also asked, what about a buy and hold strategy for 30 years as a benchmark?
Yes. Buy and hold, I'm sure at some point we looked at that, but I mean, buy and hold is basically 100%. Oh no, it's yeah. Well, I mean, buy and hold, you don't have rebalancing. I'm not so sure. I almost think that at some point we looked into that too, but I don't. My belief is that strategy doesn't pair well, but I should double check before I say that. Yeah, I think the industry strategy is a couch-potato strategy, as a constant proportion strategy, most popular ones. Yeah, that's we compared with. Yeah.
I see a question from Chris. Chris says, let me see. Sorry, I missed it maybe on slide 26. But is there an intuitive explanation for median deviating from the trend of mean initially in the shape of the distribution of outcomes?
That's a good question. Is there intuition? Yeah, that's a good observation. I haven't thought about that. I don't have a quick answer to you. So I will think about that, and I maybe and possibly discuss with my colleagues if they have some. Hey, is Peter there? I'm not so sure if Peter is there. If he's there, he can jump in. The answer is no, I don't have a quick answer. So, but it's an interesting observation. Yeah.
And then I see Eduard asking, could we use the upside values of the wealth to buy the guarantee, a put option from a third party? The third party will hedge it dynamically. We could implement the dynamic hedge strategy ourselves without buying from a third party, at least for the two asset case.
Okay, so we have not considered that. We maybe consider, well, but it's a very interesting question because one of the something related to your question, maybe I can comment on. So one of the co-author, Ray, is from the asset allocation fund from Nürnberger. And they are very much interested in looking at a put strategy and in combination with trend following strategy. So we did do some work of looking at a combination of put strategy and a trend following strategy in some way, but maybe not specific as what you're asking is to put, you want to consider the put strategy as well as the risky asset, all in combination, all of them as an asset allocation problem. We probably did some version of that, yeah. Yeah.
Okay. Carlos asks, how do you expect the neural network technique to scale with the dimensionality? Suppose you add inflation or any other factor in.
Right. So let me see if I can go back here. Yeah. So currently we have a postdoc and a PhD student. We are working on higher dimensional problems involving other factors. So the neural network training optimization, right? So as you have more feature variables, that is my D here. So essentially, it's a linear with respect to the number of features, right? It scale up linearly with the number of features. Yeah, so if you just do gradient descent, if you do Hessian descent, it will scale quadratically with the number of features. So there are a few ways that computational cost can grow. One is number of assets, number of features. So they scale up linearly or quadratically.
All right. Thank you very much. I think that concludes all the questions for you, Yuying. So thank you very much for answering them, and thank you very much for your presentation. And this concludes the workshop. So I'd like to, and first of all, it concludes the afternoon session, at least in Central European time, and it concludes the complete workshop. So I'd like to thank all the speakers for their nice presentations, very nice slides, very well prepared, and for answering all the questions. I liked the setting, despite that we are not face-to-face. I like the fact that we are very international and that we have people attending from all over the place. So thanks for that. I have in the meantime received all the slides from all the presenters. And so I will, on my own website, I will give a pointer to where the slides can be found. And also we have recorded all the presentations. So for those people who could not attend, they will get a pointer where, or if you would like to see it again, you will get a pointer where on the CWI YouTube network, the presentations can be found. So with this, on behalf of my co-author, Christopher, and myself, I would like to thank you for attending. And I'd like to thank you for asking these interesting questions. And we close the meeting. So thank you, and enjoy your evening if you're Central European time, or if you're in Asia, and enjoy your morning and afternoon if you're in American time. And see you soon, some other time, face-to-face. Bye-bye.
Thank you, Kees, for organizing this.
Thank you, Yuying.
Bye-bye.
Bye-bye.